This is question number 40 in chapter 7 of the textbook. It reads, a radioactive nucleus is at rest. It decays into a second nucleus, an electron, and a neutrino. So there are three particles. The electron and the neutrino are emitted at right angles to each other and have momenta of 9.3 times 10 to the negative 23rd kilogram meter per second and 5.4 times 10 to the negative 23 kilogram meter per second, respectively. What are the magnitude and direction of the momentum of the second, or the recoiling nucleus? So I've made a sketch here. I think that's really important. We have the original nucleus before it's at rest, and it splits into three particles. The decay nucleus, which is the large green one, the neutrino, the blue one, and the electron, the red one. And just looking at the sketch right off the bat, we should be able to kind of like identify that. So we can say that the neutrino has a momentum that's in this negative x direction. By convention, the electron also has a negative momentum. It's in the y direction. And perhaps to be a little bit more descriptive, I'll say that's a y momentum because it's in the downward direction, and that's an x momentum. Likewise, I could resolve the momentum of the nucleus into x and y components. So I could say that there's kind of an x component of momentum. So this is momentum of the nucleus in the x direction, and that I also have a momentum in of the nucleus in the y direction. I should recognize that since the momentum in the system originally was equal to 0, the sum of all the momentum of all the different particles are only 1 is equal to 0 because it was at rest, then after the collision that should also be true. The sum of all the different in the momentum must also be 0 after that collision. This is a conservation of momentum statement. So therefore, when I look at all of these, I can say, hey, look, this y component of the momentum of that nucleus is going to be equal to the negative y component of the electron, the momentum, and the x component of momentum of that nucleus is going to be equal to the negative x component of momentum for the neutrino. And so now that I've created that diagram and established those kinds of initial conditions, I can say that the momentum of the nucleus, the actual momentum of the nucleus, is going to be equal to, well, I have a right triangle here, so I could move, if I wanted to, the y momentum here over to the right-hand side. So I have this right triangle of interest where I'm looking for this side of the triangle C. Let me write that out in red so you can see it a little bit more clearly. So I have sides A, B, and C, and so I have, the Pythagorean theorem, c squared is equal to a squared plus b squared, where sides A and B are the components of the momentum that I actually know because I have already established that this piece here is equal to this piece. Let me go ahead and write that off to the side just to make it a little bit more clear. So I can say that the momentum of the neutrino, which I'll call P sub n, is equal to the magnitude of the x component of momentum of the nucleus. And likewise, the momentum of the electron is equal in magnitude but opposite in direction to the y component of momentum. Technically speaking, I should put some negative signs in here to get away from only looking at magnitude. Either way, I'm ready to deal with this, and so I can say that's equal to the momentum, the x component of momentum of the nucleus plus the y component of momentum of the nucleus. Now, let's not forget to kind of square all of these things. And so now I can say that the actual momentum of this nucleus is equal to the square root of the x component and the y component squared. But rather than put in things I don't know, let's go ahead and use these relationships over here and substitute those in. So now I'm going to get the momentum of the nucleus. And if I wanted to be technical about it, I could put that negative sign in here. But it's going to be squared, so it's just going to cancel out. And I'm going to put that number in. Well, for now, I'll just put in the momentum of the nucleus plus, and I need to remember to square it, plus the momentum of the electron. And I need to remember to square that. And then so now I can say that the momentum of the nucleus is going to be equal to the square root of 5.4, and these were just given outright to me. I didn't even have to multiply mass times velocity here. 5.4 times 10 to the negative 23rd. I'm going to leave the units out here, but it should be kilogram meter per second squared. I have to remember to square that, and to it I'm going to add the 9.3 times 10 to the negative 23rd. I have to remember to square that. And the momentum of the nucleus, at least its magnitude, this is the recoiling nucleus, the one that I've drawn in green, is 1.08 times 10 to the negative 22nd. And our units are kilogram times meters per second. Now, that answers the question, what's the magnitude of the momentum? But we also have to answer the question about the direction. And so I can recognize that that can be solved with the tangent function. So I'll say that the inverse tangent of the ratio of the y component of momentum of the recoiled nucleus over the x component of momentum for the recoiled nucleus. I'm going to make the same substitution here. So of course that's the inverse tangent. Instead of using py and px, I'll use p neutrino and p electron. So that ends up being 9.30 times 10 to the negative 23rd units. Again, I'll leave those units out, divided by 5.40 times 10 to the negative 23rd momentum units. And when I run that through, I get an angle of theta of about 60 degrees. It ends up being 59.9 degrees. And I think I actually have 3 sig figs here. Yep, I do. So this angle theta is about 60 degrees. And so then my final answer is going to be the momentum has a magnitude of 1.08 times 10 to the minus 22 kilogram meters per second at an angle of 59.9 degrees.